So this section is about base solutions. So like the definition for strong acid, a strong base is one that dissociates completely in solution. So when that happens, the hydroxide ion concentration is equal to the concentration of the base. Most strong bases are either alkali or alkaline earth metal hydroxides. So these are all ionic compounds. When they dissolve, they separate completely into ions. Now, some of these have limited solubility, but that's different than a weak base where you have intact molecules. You just have solids sitting at the bottom. So pretty much if you see a metal with hydroxide, good chance that's a strong base. So the group 1s, because they have a +1 charge, they will form 1 mole of hydroxide for every mole of base. The group 2 have a +2 charge. So you're going to get 2 moles of hydroxide per mole of base. So you need to watch out for that. So here's strontium hydroxide. When this dissolves, we get 2 moles of hydroxide ions. I will try to trick you with a question like that. Absolutely. One of my favorites. And bases are different than acids. A diprotic acid like sulfuric acid, the first proton is a strong acid. It dissociates completely, ionizes completely. The second one is weak. So the first one comes off, and then the second one comes off. Those are molecular compounds that are ionizing. These are ionic compounds that are simply dissociating. They're dissolving. So they do it all at once. And it's these group 2s that are only slightly soluble. What about weak bases? Weak bases are like weak acids in that they do not form, well, it doesn't really work that way. We'll just go with what it says here. So the common weak bases produce hydroxide ions, not by having a hydroxide ion themselves, but by accepting a proton from a water molecule. A proton is a hydrogen ion. So if the water here gives up a hydrogen ion to the base, what we have left is the hydroxide ion. Hydroxide ion was formed by the base, but this hydroxide did not come from the base. Does that make sense? So that's a little different than how weak acids work. The most common weak base we'll see is ammonia, NH3. You look at that, and that doesn't look like a base, does it? There's no OH in it. It's because it's a weak base. So NH3 ammonia will accept a proton from water and form ammonium ion and hydroxide ion. This is an equilibrium, and if I remember correctly, it lies mostly to the left. So this reaction does not go to completion. There's a lot of the intact weak base in the solution. That's why it's weak and not strong. So the base ionization constant, Kb, quantifies the strength of a weak base. So the chemical equation here is the base plus water forming the conjugate acid plus hydroxide ion. Water is a liquid, and so it does not show up in the equilibrium constant expression. So we've got BH plus concentration times hydroxide ion concentration divided by the base concentration. Smaller Kb means a weaker base. So larger means a stronger base. And often we'll use pKb because the kb's are these kind of outrageous numbers, 10 to the minus 7 or 10 to the minus 12 or something. They're messy, just like hydrogen ion concentrations. And so when we put the p in front of a variable, that p stands for negative log of. So pH is the negative log of the hydrogen ion concentration. pKb is the negative log of the base ionization constant. So here are some common weak bases. This is just kind of like a mess of a table. We see the names and formulas of the weak bases over here, and their KBs are listed over there. And then this shows the ionization reaction. So in each of these, we see the base reacting with water, and we end up with a hydroxide ion as the product. Several of these are relatives of ammonia. There's probably a slide later that's going to talk about it, but I'm thinking about it now, so here goes. So methylamine is, so here's ammonia. Methylamine is ammonia where we've substituted one of the hydrogens. So instead of, say, this hydrogen, we've got something else in there. This methyl group, CH3. That changes the Kb, it changes some of the properties of it, but it still acts as a weak base. Here, ethylamine, we've got ammonia with an ethyl group substituted in. Here's ammonia. These are two other ones, pyridine and aniline. They have nitrogens in them. So if you see a compound with lots of carbons and hydrogens and a nitrogen in it, is probably a weak base, because it's this lone pair of electrons that causes it to act as a weak base. We also have a couple other ones in here that don't look like bases: carbonate ion and hydrogen carbonate or bicarbonate ion. So carbonic acid is a diprotic acid, and it loses hydrogen ions to form first hydrogen carbonate ion and then ultimately carbonate ion. But because it's a weak acid, these ions act as weak bases. So they can take a hydrogen ion from water and remake the other ions. So that can remake the ion here, and here it remakes carbonic acid. Yep, there it is. So Lewis structure for ammonia, we've got this lone pair. And here we've got water. So what happens is that the hydrogen ion, it's only a proton. It leaves its electron with the water, and the proton goes over to the ammonia. And so now this has a positive 1 charge, this has a negative 1 charge. Nitrogen still has an octet of electrons. Oxygen still has an octet of electrons. Here's methylamine. Again, that's ammonia with a methyl group on it. And this acts in the same way. We've got this lone pair of electrons, and a hydrogen ion can come over here. The hydrogen ion, being just a proton, doesn't have any electrons to form covalent bonds with. It can't do that. But nitrogen is willing to supply both electrons for a bond. And that's called a coordinate covalent bond, where one atom is very generous and donates all of the electrons, and the other's just kind of a mooch. So, as with strong acids, with strong bases, there is autoionization of water, but the contribution of it is so small it's negligible, we can ignore it. So, for weak base solutions, we're going to have a similar process that we did with the weak acid. We're going to neglect the contribution of the autoionization of water because we can usually do that with weak bases as well, unless they're very low concentration. We need to make an ice table, and we need to use the Kb expression to find the hydroxide ion concentration. Then if they're asking us for pH, we're going to have to convert to pH. Okay, so this one's a strong base, barium hydroxide. It also says strong base right up there. So it's asking for the hydroxide ion concentration and the pH. Well, it's always a good idea to write the equation. So barium hydroxide is a solid, no, sorry. It is, no, I think we do put it down as a solid. It ionizes completely and forms barium ions and hydroxide ions. How many hydroxide ions? Two. Because each barium has 2 hydroxide ions. So if we started out with 0.010 molar, and this is a strong base, it's all going to dissolve. How much barium ion are we going to get? 0.010. And how much hydroxide ion? Yeah, 2 times that, right? You can think of this as being a bicycle, where the barium is the frame of the bicycle and the hydroxides are the wheels. When you take the bicycle apart, you have 1 frame and 2 wheels, right? You have twice as many wheels as you had bicycles. So that's how these work. Okay, so the hydroxide ion concentration then is this. We didn't really have to do much to find that. But now it's also asking us what the pH is. So there's the circle of pH. And you can go around the circle in either direction. You could start at any point. What we have here is hydroxide ion concentration. I guess I should put the brackets on these guys. We have hydroxide ion concentration. We go on to get a pH that's directly across. So you can go through POH to pH, or you can go this way. Whatever seems easier to you. I prefer to go this way. Finding the POH is just the negative log of our concentration. Negative log of 0.020. How many significant figures does 0.020 have? That's 2. So that means that my POH should have 2 decimal places. Oftentimes I'll write down 2 extras. This one, it goes 897 and then a bunch of zeros. And so it's like, well, let's just write 3 of them. So that's the POH. The relationship between pH and POH, they add to 14, right? So the pH is going to equal 14, exactly 14, minus the POH. .30103. And again, we want 2 decimal places. So our answer is the pH is 12.30. So that's one answer, and this is the other answer up here. Any questions? It's the 2 you have to watch out for. A weak-base solution. Find the hydroxide ion concentration and pH of a 0.33 molar methylamine solution. That gives us the Kb. We do not need to know what the chemical formula for methylamine is. You can look it up if you like, but we can just call it B for base. So the first thing we want to do is write the ionization reaction for this weak base. So we have our base plus water will be in equilibrium with the base takes a hydrogen ion and leaves the water molecule as a hydroxide ion. And then we can use that equation as the header for our ice table. So we're going to look at the initial concentration, the change in concentration, and the equilibrium concentration. So this tells me that the initial concentration is 0.33 of the methylamine. That's B. Water doesn't come into this because it's a liquid. What's the initial concentration of BH plus? 0. And how about the hydroxide ion? Approximately 0. So we're going to use X to indicate the amount of change. We don't have any coefficients other than 1s here, so it's just going to be minus X's and plus X's. So this one will decrease in concentration by an amount X. So this will change by minus X. This one will change by plus X. And this one will change by plus X. So at equilibrium, we're going to have 0.33 minus X and X and X. So Kb equals 4.4 times 10 to the minus 4, which equals the concentration of the products multiplied divided by the concentration of the reactants, but not water because it's a pure substance. And then we can plug in our equilibrium values here, and we get x squared over 0.33 minus x. We could use the solver, or we could use x is small. Let's try x is small. So if x is small, that goes to 0, and then x is equal to the square root of 0.33 times 4.4 times 10 to the minus fourth. .0120. How do we test that to make sure that x is small is appropriate? Yeah, we're going to divide x by what we are subtracting it from to see if it's less than 5% of it. And it is. It's 3.7%. Yes?
How do you get the non-negative x?
That's a good question. Start with 0. So instead of starting with some other number, start with x is 0. And that's what you positive. Yeah, there's two roots to this problem, to this equation, right? One's positive and one's negative. Any questions about that? So what does x represent? It's the hydroxide ion concentration. Kind of took up the whole slide here. The pH then is equal to 14 minus the POH. Sometimes I just do this on my calculator. POH is negative log of hydroxide ion concentration. There's two negatives there, so it ends up being 14 plus the log of hydroxide ion concentration. That doesn't make sense, just, solve it regular. Again, we should have 2 sig figs, so 2 decimal places. Getting 12.07918. So we call that 12.08. Questions?